Hi, my name is Aubrey Goff, and this is my comparison of the computational and experimental models for Lab02 motion of a falling object. So I use Tracker to extract real-world motion data from a video of a falling object that you can see here. And I built a simulation model of the same event, and I'll compare a gravity only and a gravity and drag computational model to the real data. So my tracker data showed a ball initially located around the origin, and using the first two changing data points, I calculated an initial horizontal velocity of 0.956 meters per second and vertical velocity of 1.914 meters per second. And then in the computational model, I used this velocity to start the simulation, and I modeled two scenarios. So the first scenario that we're going to look at is going to be with b equal to 0, meaning that there is zero drag and the only force working in the y direction is gravity. So this is what this model is going to look like. And here we can see our position versus time and our velocity over time graph. You can see a parabolic motion in the position versus time and a linear motion in velocity versus time. And when we include drag into this, when we change our b value, it's going to look something like this. So in the gravity-only model, the object followed a perfect parabolic trajectory, and it kept accelerating throughout the fall. And then when this is put up against the tracker data, the model actually overshot the motion, particularly during the descent. It doesn't really reflect how objects really move in space and time. But in comparison, this model, the second one that includes drag, produced a trajectory that was closer to what we saw in our initial tracker video, and it rose and fell more slowly. It reached a lower peak height that was similar to what we observed in the video. So this kind of confirms that drag is necessary for modeling real-world motion accurately, especially when it's thrown at certain speeds. As far as terminal velocity goes, terminal velocity occurs when the net force is zero. So when the drag force is equal to the gravitational force and acceleration stops. So in my simulation with drag, I observed the velocity versus time graph, you can see here, begin to flatten here during the descent, which means that the object was actually approaching terminal velocity. But in contrast with the gravity-only model, which if we go back and look at here, when we look at our velocity over time graph, we don't see a gradual decline. So in contrast, the gravity-only model showed a continually increasing velocity, which would be unrealistic in real life. So if we clearly wanted to observe terminal velocity, I could use a longer fall or a taller drop height, or maybe an object with a larger surface area. And then if the object were thrown straight up with the same initial speed of about 2.14 meters per second, it would take longer to hit the ground than the original case, because the resistance slows the object on the way up and on the way down. So without drag, the time up equals the time down, and the total time is shorter. But with drag, both parts take longer due to the opposing forces of air resistance, and this can be seen in the equations of motion with drag, or verified computationally by modifying the velocity models. So in conclusion, the gravity-only model was a bit too simplistic to represent real motion, and a computational model that includes drag better matched the data that we saw in Tracker, and overall helped me understand how to construct physics-based simulations and how important it is to include all relevant forces when modeling real-life systems. Thank you for watching.